Hey YouTube, this is Maxwell and welcome back to Animating Physics with Python. This is part 3 of the Projectile Motion series, and in this video we will actually see some projectile motion. Our animation should be done and it will be cool to look at and test it out. And to give you guys a little bit of preview, like I did last time, this is how it's going to look like. We'll be able to enter initial velocity and an angle. We'll be able to click the start animation button and it will move and like something that has been thrown. So let's get to our code and actually do this. So first thing we're going to do is hop on over to our configurations frame, and we're going to define two functions that will allow us to get the initial velocity and the angle set by the user. To do that, first I'm going to make a get initial velocity function and have it return the initial velocity. This really should be written like this. I don't know why I used camel case there. Dot get. It should be in camel case. Be consistent with how you write variables. And next is our angle. We're going to take our angle and we're going to return it. Easy stuff. But for actually with Python, we have to work with radians, which is another way of measuring angle. So when our user gives their angle in degrees, we're going to convert it to radians. Now, we're also going to create a function to make the start animation button functional. So this will let us give it the necessary function for it to perform its duty and actually start the animation. So we're going to create a set button command function. We'll be able to pass in the animation function. We're actually going to need to give this button an attribute, or set it as an attribute, so we can refer to it in our function. There. Now we can refer to this button here, call its configure method, and give it a command, which will be start animation. So that is our configuration frame is done at this point, and we can move on to the window class. There is not much to do here either. All we need to do is create a function that will start the animation and then connect that function to the start animation button. So we're going to create a function called start animation. And what it's going to do is going to get the initial velocity from our configuration frame, and it's also going to get the angle from our configuration frame. And then is going to tell the canvas to start the animation. So because our canvas will handle the animation, all we're going to do is give it the initial velocity and the angle that the user set, and let it handle it. And so we haven't made the animation yet, but we haven't made this function yet, but we will in a moment. And so the last thing now is in our init function. With that function we created called setButtonCommand, we can connect our button to this start animation button, like this. And we can actually test if this works when we click the button. So I'm going to have this animation function actually print initial velocity and angle. We're gonna see if it actually gives us back those values. Oops. Or I use Oh yeah, okay. The animation button. I'll give it the wrong name. And boom. So we'll set our initial velocity to 10 and angle to 90. We'll click this button and it should print 10, and it gives us 10, our initial velocity, and this 1.570, which is going to be 90 degrees in radians, which is what we wanted. So that works. And we can remove this print and actually have it call the canvas's start animation function. And we're going to hop on over to the canvas class or animation class and actually code it. This will be the hard stuff. So in here, we're going to create our start animation function and have it take in the initial velocity and angle as parameters. Now, as the animation is going, we're going to need to keep track of a lot of information. So in this function, we're going to be creating a lot of attributes. So first thing we're going to do is get the horizontal velocity and vertical velocity of our projectile. And as we went over in part 1, we use a little bit of trigonometry to do this. So our horizontal velocity will be our initial velocity multiplied by the cosine of the angle. Our vertical velocity, and I forgot to add self here, rookie mistakes. Our vertical velocity will be our initial velocity multiplied by the sine of the angle. And I'm also going to set our gravitational acceleration to 9.8, which is Earth's gravitational acceleration, and that's what we're going to use. Now, because our animation will have the ball starting on the ground, we can use this equation to get the total time. The total time of how long the ball is going to be in the air for. And to get that, we can take our vertical velocity and divide it by 1/2 multiplied by our gravitational acceleration. Divided. Now, because this is an animation, we're going to need to redraw the ball in a new position several times. And each time we redraw the ball, that's going to be a frame. We're going to call that a frame. Those of us who game might be familiar with that concept. And so the amount of times we're going to redraw it should change depending on how long the animation will be. So for setting the total number of frames that this animation will take, I'm going to take the total time, so how long it's going to be in the air for, and I'm going to multiply it by 20. So whatever time we get for total time, I'm going to multiply it by 20. I'm going to round it because it needs to be a whole number. And that will be the total number of frames the animation is going to take. That's pretty arbitrary. 20 is an arbitrary number. You can mess around with that number and to see how it works for you and your system. Alright, we're also going to need to know what frame we're on. So I'm going to create an attribute called self.number of frames. And set that to 0. Now after each frame, we're also going to increment time, and so that our equations give us the correct displacement to draw the ball at. So we're going to create this time step attribute, which is going to be our increment for time. And we're going to calculate it by taking the total time and multiplying it by the total, not multiplying, dividing by the total number of frames. So this will mean that because our time will start at 0, by the time we get to the last frame, our time should be equal to total time. So that means our ball will be in the correct spot where it needs to be at the end of the animation. So when we get to our last frame, we'll be on our last time step and our animation should be done. We're also going to need to get a time variable to keep track of time, and we're actually going to set it to time step, so as if we already incremented it once. So when the animation starts, it already gets to moving. We're not going to start at 0, we're going to start at time step. Last attribute we're going to create is getting the starting ball coordinates. We're going to need to know at all times where the ball was at originally, where it took off from. And so to do that, we're going to call the canvas's coords method, which when you pass in some object you drew, which is the ball, which we drew up here, it will give you the coordinates of where it is in the canvas. And personally, I like setting any attributes I create. I don't like creating them in functions. I'd like to create them in the init function. So I'm going to take all the attributes I've created and create them here first and set them to none. None. Let's see. Sorry, horizontal velocity, vertical velocity. So, alright, that's all of them. And now we have all our attributes ready. We're going to call self.doAnimation, which is what we're going to create right now. So what this function is going to do, it's going to it's going to draw one frame of our animation. It will update the number of frames we're at, it will increment time, and then it will schedule itself to be called again a short time later to draw the next frame. And this will go on and on until we reach the last frame and the animation is done. This is how we're going to create the animation. You could use a while loop, but that would block. Actually, a while loop wouldn't work as it would block the tk-inter main loop and events wouldn't be updated. You could use a while loop in a thread, and that's another way of doing it as well. But I think personally this way is easier and it kind of fits in more with the tk-inter design. Scheduling a function a short time later, but it's best if I demonstrate it first. So first thing I'm going to do is check if we're on the last frame. So self.number of frames is equal to self.total number of frames. Return, and this will end the animation. It will not schedule itself to be called again. So if that is not true, we're going to move on with our animation, and we're going to get the horizontal displacement. So that can be gotten by taking our horizontal velocity and multiplying by time. If you watched part 1, you'll be familiar with these motion equations. And for the vertical displacement, it will be the self.vertical velocity multiplied by self.time plus 1/2 times our negative gravitational acceleration multiplied by time squared. And that will be our vertical displacement. Next is we're going to get the starting coordinates of our ball, which we have here. And remember that with a circle, the coordinates are actually the top left point of a square and the bottom right point of a square. And the circle is just inside it. So I'm going to unpack our starting coordinates, and I'm calling top left x to be the x, just the x component of our top left point, the y component of our top left point, the x component of our bottom right point, and the y component of our bottom right point. And that will be our starting ball coordinates. And we're going to use these points and add them add our displacement to it, which is kind of how displacement is defined. It's distance from a starting point. So we'll take, to create new coordinates, we'll create new top left x, new top left y, and set them equal to top left x plus our horizontal displacement. And then top left y, and this will be minus our vertical displacement. And it's minus because of the coordinate grid and how it works in tkinter. They put the origin 0, 0 at the top left point of the screen. So if you want to go down the screen, you actually increase the y coordinate. If you want to go up the screen, you have to decrease the y coordinate. We want to go up, so we have to decrease the y coordinate. And coordinates in tkinter have to be whole, have to be integers, so we're going to round them. The same thing for the bottom right points. I'll take drx plus horizontal displacement, dry minus vertical displacement. Nice. Now we're going to give the ball those new coordinates, and we can do that easily by using the canvas's coords method, giving it our ball, and then providing these new coordinates. X, new br, y. Lastly, we update, that's our animation here, basically. And now we have to do some like updating values. So first, we're going to update the number of frames because we've just completed a frame. We're going to update that to reflect that. So the number of frames plus equals 1. Next, we're going to increment our time. So we're going to increment it by the time step we created. And lastly, we're going to do what I talked about earlier, and we're going to schedule this function to be called again a short while later. And by a short while later, I mean a 30th of a second later. So it's not very long, but setting it to a 30th of a second later will make it so that this function should be called approximately 30 times a second, giving us 30 frames a second. So we'll solve that after. And this is in milliseconds, so I'll do 1,000 divided by 30. We'll give this a 30th of a second. And function will be this function, self.doAnimation. And that should be our animation. I know this is missing one thing, but we're going to start it and check it out, see how it works right now. And it seems like I imported something I did not mean to import. Do that. Great. Let's test it out. Well, put an initial velocity of 20, an angle of 45, start the animation. If you look at that, it's going up and down, as if it's been thrown and following this parabolic path. And it works, but it is very small, like it's moving really small. And that's because in our code, we're equating 1 meter, let's say our displacement is in meters. We're equating 1 meter to 1 pixel. And the pixels are really small. And when we're dealing with the small distances you're going to have at maybe 20 meters a second, that's actually pretty fast. But saying like in pixels, like 20 pixels, even 20 pixels is not a lot. So for any displacement we get in some distance unit, we're going to multiply it by some scaling factor, and I'm going to use 5. And so in this way, I'm kind of equating 1 meter to 5 pixels, and it should make the animation a little bit more visually appealing, or cover larger distances. And alright, so let's call this again. I haven't closed this. Now with a scale factor of 5, It should cover larger ground and look a little bit better. And see, I already like that a lot better. And you see it's going up and down as it's just being thrown. Of course, it's not the most realistic case of projectile motion. It's not showing the ball bounce later. There's no horizontal deceleration, like no air resistance, anything like that. But it is showing what projectile motion would look like in the most ideal case. And you can mess around with these values and it should work fine. See, if you put an angle of 90, it should go straight up. And it is, goes straight up. You can see it actually decelerates as it goes up and accelerates as it comes back down. Let's add a higher initial velocity, let's say 50. Boom, jumps up, ooh, almost out the screen. Should come back down hopefully, and it does, and it accelerates and hits back down on the floor. As you can see, it's a little choppy, but it's TK Inter. And maybe if you have a better system, it'll be a little bit smoother. You can also mess around with this value. This sets maybe frames a second. You can mess around with this value to see if you need more frames or less frames for a given animation. So you can mess around with those values to see if you can make this look a little bit smoother. Or we can mess around some more. Let's say a really low angle. Give it an initial velocity of 30. See how that looks like. See, it's pretty good. Actually, turned out pretty well. So thanks for sticking with me throughout this series, and I hope somebody might take something out of me making this. The code will be posted on GitHub, which will be linked in my description. And there's still lots of things to do with this animation. I have no way of resetting the ball back to where an original position, so we can have more space to do it. Once it goes out the screen, it's gone. It's not resizable friendly. It's not resize friendly. So there's lots of things you can do to improve on this. And if this video gets traction and people ask for it in the comments, if that actually happens, I'll actually consider completing this, making it a little bit better. But for now, this is it. And anybody who wants to fork this on GitHub and extend it is welcome to. It'd be pretty cool to see. And see you later.